Well, we're very happy to have Tien-Tien Yu from the University of Oregon. She's going to talk to us about BBN constraints on ultralight scalars.
Okay, well, thanks for the invitation to come here. Sorry if I'm a bit clogged up in my nose. I usually don't sound so stuffy. So this is work that I've been doing with Philip Sorensen, who is finishing up his master's at CP3 in Denmark, and will be starting a PhD at DESY with Geraldine Servant. And he was a summer student at CERN last summer, and with Sergei Subirokov, who is also at CERN. So this is a work in progress. What I'm showing you is all done, and we're finishing it up, but that is to say, feedback is very welcome. If you have any complaints or you see something that you're like, oh, this doesn't make any sense, please let me know. That would be very good to know. Okay, so I'm going to talk about constraints from BBN on ultralight scalars. So why look at BBN? So here's a picture of the history of our universe, where we are today, here. And we started off with the Big Bang. And so we go through this process where we have the Big Bang, we go through inflation, and then we have all these this hot, dense plasma, which slowly starts to cool down because the universe is expanding, and then we form nucleons here, which then combine together to form larger atoms. And then here we hit the cosmic microwave background, which is sort of the surface of glass scattering. And then slowly we can start to form even larger structures until we end up today with us. So the BBN is looking at this, it's really hard to see, at this stage here. So the reason why BBN is an interesting way to probe new physics is that you can predict all the elemental abundances in BBN using known physics. This is very well-known physics. And in fact, using what we know, we can extrapolate back, and it matches up or we extrapolate forward, and it matches very well with observations. So BBN is a kind of a very robust way to test new physics, meaning that any small deviation in this period of time will have very large effects now, or will have noticeable effects now. So if you wanted to probe new physics, here BBN is a very sensitive probe to that. So just a few standard facts about BBN. So BBN is Big Bang Nucleosynthesis, just to be clear. And it takes place during the time period of about 0.1 to 1,000 seconds after the Big Bang, which corresponds to temperatures of a few MeV to 10 keV. So as we go down in temperature, it means we're going forward in time. So what do the predictions of BBN depend on? So I was saying it was very kind of robust theory. We know all the pieces that go into it. So what it depends on are the number of neutrino families. So this kind of gives you this N effective, which then tells you what you expect the Hubble rate to be. So how fast the universe is expanding. It depends on the neutron lifetime, so we'll see where that comes in the next few slides. It depends on the baryonic density, so how many baryons we have compared to the number of photons. And in fact, this is basically the main thing that sets what the abundances are. And it follows from a well-understood sequence of events, meaning it follows from various nuclear reactions that we know about that give the abundances. So what elements are formed during BBN? Well, the Big Bang Nucleosynthesis forms most of the currently observed helium-4, deuterium, helium-3, and lithium-7, and maybe a few more of those. So it forms all the light elements. So these are formed in the early universe. Heavier elements are formed in other situations. For example, they're formed in the stars, or for example, neutron star mergers. It's proposed that this is where gold is coming from. So the light elements are formed during BBN. And in fact, BBN forms, I think, all of helium-4. So the thing that we calculate when we talk about BBN are the elemental abundances. So by elemental abundances, I denote that by this Y sub I. It's the number of atoms of that element compared to the baryon number density. So it's the fractional density of that particular element I. And so I, in this case, is P, or hydrogen, neutrons, deuterium, helium-4. And so the evolution of these abundances follow this equation here. So the change in the abundance depends on the Hubble rate, so how fast the universe is expanding, and also depends on the decay rate of these different elements, as well as the rate of converting from one element to another. So these are where all the nuclear reactions fit into play. Okay, so through this, we can calculate what we expect the elemental abundances are. So let's start at, so I was saying BBN was between a few MeV to tens of keV. So let's start at the hotter end. So let's look at when temperatures are above 1 MeV. So when temperatures are above 1 MeV, the weak interactions are keeping neutrons and protons in thermal equilibrium. So what I mean by this is that these reactions that go back and forth between neutrons and protons, the weak interactions, are allowed to go in both directions. And then you have electrons and neutrinos depending on which process that you're looking at. And so through this process, this tells you what the ratio of the number of neutrons versus the number of protons are. And what this ratio depends on is the mass difference between neutrons and protons and the temperature that you're sitting at. So this is just a thermal distribution of neutrons and protons. Okay, so we have, when we're above an MeV, we have this rate. And so you can see here, if neutrons and protons were the same mass, you would have the same amount of both. But they're slightly different in mass, so we have a change. Okay, so this process of the weak interactions continues up until a certain point, until a freeze-out point. So how do we calculate when does this freeze-out stop? It stops when the rate of neutron to proton conversion is smaller than the Hubble rate, meaning that the universe is expanding faster than this rate can occur. And so this rate, these weak interactions go like the temperature to the fifth and the Fermi constant. And so we want to compare this to the Hubble rate, which goes like temperature squared. So we can equate these two things together and get what we call the freeze-out temperature in terms of these parameters. So G star here is the number of relativistic degrees of freedom. And this is what I was saying, it depends on, for example, the number of neutrino families. So plugging these in, we can figure out what the freeze-out temperature is, and that's about 1 MeV. So at 1 MeV, the weak interactions stop.
This is assuming an S-wave interaction or a P-wave interaction for G to the power of 1.
For which one? For this?
Yeah, S-wave interaction or a P-wave interaction or an exterior globe.
So this is just the weak interaction. So I think what you're thinking about is dark matter annihilation,
Yeah.
which depends on the velocities.
Yeah.
So it's slightly different. Okay, so at this freeze-out temperature, these weak interactions stop, so we freeze out the ratio between neutrons and protons. Right? So it's this exponential that depends on the mass difference and the temperature, and now we can plug in the freeze-out temperature. And if we plug in the mass difference between neutrons and protons and 1 MeV, this gives us about 1 neutron for every 6 protons. So 1 neutron here, 6 protons, 6 protons over there. The ratio isn't actually quite 1/6 because even after freeze out, the neutrons can decay still. So the neutrons can go in this direction. And so this 1/6 is actually more like 1/7. So we have 1 neutron for every 7 protons. So now we have a fixed number of neutrons, we have a fixed number of protons. So we can start forming elements. So, well, of course, we have more protons than neutrons, so all the neutrons will want to pair up with the proton and form deuterium. However, we're still at high enough temperatures such that we're surrounded by this photon path. We're surrounded by photons, and these photons are energetic enough to break up deuterium. And so, in fact, we can't form the heavier elements until we can form deuterium. But we can't do that until the photons are low enough energy to stop breaking up the deuterium. So this is what's known as the deuterium bottleneck. So it takes some time before we can form deuterium, which then goes into tritium and then into helium. So this is how we break up the deuterium with the gamma. So the point I wanted to make here is that this process ends up with helium. The helium is very stable. So what this means is that all of the free neutrons. So remember, there's one neutron to every 7 protons. All of those neutrons are going to end up in helium. So pictorially, this is what's going on. So on the x-axis is the temperature in keV. You can convert that to time on the top in seconds. And the y-axis is abundance, the relative abundance. So this top line, H, is hydrogen, number of protons, and the number of neutrons is this dashed line here. Conventionally, we call the helium abundance Y sub P, whereas all the other ones are labeled by their, what you would expect. So D is deuterium, 3, He is helium 3, it's tritium. So here we see we have neutrino decoupling. There's supposed to be bars here. You can kind of imagine where they are. So here, and then we freeze out neutrons and protons, and we form deuterium. However, because we are still above the deuterium binding energy, meaning the photons are above about 2 MeV, is the energy for deuterium, we can't form the heavy elements until we go below that temperature. So okay, once we hit that point, so here's the deuterium bottleneck. Once we pass that, then all of a sudden all the neutrons go into helium-4, and then we have some deuterium, and then the other ones are less. So I want to really focus on the helium-4 formation in particular, and how that's affected by new physics. But let's go back to helium-4. So I was saying all the free neutrons end up in helium-4, and that the neutron to proton ratio at this freeze-out time is 1/7. And so you can calculate, just in 2 lines, that the helium-4 abundance only depends on the neutron to proton ratio in this with this relationship. And this is about 1/4. So helium-4 makes up about 1/4 of the elemental abundances. And so you can maybe start to see here that because it only depends on the neutron to proton ratio, if you want to change the abundance of helium-4, you want to change this ratio. And looking here, you can do this in a few ways. You can change the mass difference between neutrons and protons, or you can change the freeze-out temperature. And to do either of those, you can put in new physics. And so in particular, I want to look at changing the freeze-out temperature. And so how do I want to do it? So based on my title, I want to look at ultralight scalar particles. So I have a very brief aside into dark matter. So one reason why ultralight scalar particles are interesting is they could be a potential dark matter candidate. And I think you all are familiar with the fact that we think there's dark matter out there. It interacts gravitationally. But beyond that, it's pretty fair game. So it can span a huge range of masses, or dark matter candidates, from 10 to the minus 22 electron volts up to hundreds of TeV. So by ultralight, I'm thinking about things that are in the EV and below mass range. And in particular, I'm thinking about ultralight scalars. We also have pseudoscalars, so these would be like axions and helps. I'm going to focus on scalars for this talk. Okay, so what does our ultralight scalar look like? So we want to describe everything with a Lagrangian. So I just have my scalar Lagrangian, so my kinetic term, and I give it a small mass of m5 squared. And I want to consider a very kind of general case. In the future, you can probably look at some more specific things. But for simplicity, I want to think about a scalar with universal couplings. And what I mean by this is, you can think of this as being some conformal transformation of a metric. So I take my metric, and I conformally transform it by this alpha term. And this alpha depends on phi. So it's phi squared over some scale lambda squared. So I'm not going to say how I get this this conformal transformation, and why we're going to do it. I'm mostly interested in saying, suppose I do have this, what is the effect on BBN? So by looking at this scalar with universal coupling, the Lagrangian of the standard model gets modified. And it gets modified in the following way. So we start off with our standard model Lagrangian, and by adding in this piece, by giving it universal couplings, this manifests itself as a phi squared over lambda squared term multiplying the mass terms in the standard model. So the fermion pieces get something that goes like phi squared over lambda squared mf bar, and the vector pieces get one with the opposite sign.
Why is it different than the dilaton case?
So the dilaton is a linear. So, but yes. So
So you
I
would
don't
have
know
got,
if-
right, with a dilaton, you would have got 1 power of 5 for each mass, so that it would be linear coupling to fermion and squared coupling to E squared.
So if I understand correctly, the dilaton is this, but the alpha is a phi over lambda.
Never mind, go on with that.
Also, the
It
dilaton
should be-
would expand around some non-zero bed. Here, you're presumably expanding around phi equals 0,
Yes. Yes.
right? And phi equals 0 is not scales going to infinity or 0 or anything funny.
Yeah. So previous work who had done, who have looked at these ultralight things, they usually put it in the context of the dilaton. So this is slightly different. You could do the same exercise that we will be doing with the dilaton, which could be a future project. Okay, so point with being here is we have the standard model and we have these extra pieces where we have now a phi squared coupling to the fermions and to the massive vector bosons. So what this means is that the fermion masses get an effective mass. So you remember we had these extra pieces that went like phi squared over lambda squared. So the fermion masses change by this quantity 1 plus phi squared over lambda squared. But because we're looking at these phi squareds, a phi squared piece, this also means that the scalar mass gets modified. So the scalar will also have some effective mass. So this m phi squared will go to m phi squared plus something that depends on the fermions and the vectors. And for our purposes, because in the times that we're thinking about around BBN, I'm going to neglect so this is the density of fermions and the density of vectors. And around the time of BBN, this is negligible, so I'm going to cross that out. I'm going to say this is the density of baryons in the early universe. So the next thing we care about is the scalar evolution, because we want to say that this phi is the dark matter now. But the effect that it's having on BBN is in BBN, so I want to know what the field looks like during BBN. So I need to know how it evolves with time to run time backwards back to BBN. And so the scalar evolution is given by standard equation here, where V prime of phi is the derivative of the scalar potential. And you started off with V of phi of just the mass term, but now we need to change it to be the effective mass. So it's more or less the same thing, but now the mass is, instead of m phi, is m phi effective. So plugging this into our Hubble equation, we get that the evolution of phi follows this piece that goes like the second time derivative of phi, Hubble friction term. This is a standard. A bare mass term. So normally we think about just this when we're talking about scalar evolution. Now we have this new piece here that depends on lambda squared, capital lambda squared, and the baryon density. Okay. So now we can try to solve this to figure out how phi evolves. So there's one more piece that we need to understand, which is how the baryons also evolve with time. So let's take a quick look. Baryon density. So we can calculate what the co-moving baryon density is. So this is part of a lot of things. The most important piece to pull out here is that the co-moving baryon density depends on the number of relativistic degrees of freedom. So we can calculate what it is, and then we have to integrate over some distributions. And then we can get the physical baryon density by multiplying it by the scale factor, the minus 3. So we need to know what the relativistic degrees of freedom are at a given time. So we can calculate this. This is known. So here's a plot on the x-axis here. You can see is the scale factor. It's the log of the scale factor. And on the y-axis is the baryon density. So now you would expect, because we're thinking about baryons, which are matter, it should go like a cubed, or 1 over a cubed. So that's this dashed line here. But in fact, when you hit around the electron mass, you need to take into account that you have electrons and positrons that are relativistic. So it actually changes the distribution of this little key up here. So now we have our Hubble equation that tells us the phi evolution, and we also know how rho sub b evolves with scale factor, which is equivalent to how it evolves with time. So let's try to solve for the scalar evolution. So we have our equation here. So this is not easy to solve. So one way to simplify our lives is to consider the different phases when each piece becomes dominant. So, right, so the kind of the two free parameters that we're interested in are m sub phi and lambda squared. So depending on what m phi and lambda are, one of these pieces is going to be the dominant piece. So what we do to simplify is to consider only the dominant term, and through that, turn the crank and figure out how phi evolves with time. And so there's two phases that we want to think about. We want to think of when things are radiation dominated and when they're matter dominated. And the three different terms are going to be the Hubble piece, this what we call the bare mass piece, and the capital lambda piece. So when we go through and solve it, what we're doing is just turning off all the pieces except for, in this case, so we leave the lambda piece on, solve for that. We get this dependence on the scale factor. For this one, we turn off these two. We solve for that, and then in the Hubble case, okay, we don't have this potential, so nothing changes. So for a specific example, let's suppose that the evolution goes such that in late times, you're dominated by the mass, and then in some intermediate time, you're dominated by the lambda piece, and in early times, you're dominated by Hubble. So the evolution of phi is going to first now look like a to the minus 3 halves. In some intermediate stage, it'll look like a to the minus 3 fourths, and early times it'll look like a naught. So then the value of the field at BBN is just the value of the field now, times this a sub b, which is where it changes between these two phases, the minus 3 halves, and a sub lambda, which is when it changes between these two phases, over a sub b to the minus 3 fourths. So now we can evolve our field backwards. So we know what this value is, and we wanted to figure out what this value was. So this is just one specific example. And so just to give you kind of a picture of how things look. So I was saying the scalar evolution depended on the relative sizes of m phi and capital lambda. So here's a plot of m phi on the x-axis. This is the scalar mass. And the scale factor, lambda, on the y-axis. So when we're in this phase here, these two pieces are small. We can neglect them, and we're dominated by this piece. And also like this here, this is this, I think this corresponds to this one. But yeah, so in this way we can figure out what the evolution is. And so when you do the calculation, you say, okay, I pick a certain m phi and lambda point, I see where I sit, and then I can figure out what my scalar evolution is at. And so you can make a little grid of m phi versus lambda and figure out what phi BBN is for that parameter point. Okay. So how do I use this to figure out what the helium-4 constraints on this scalar are? So I've been talking a lot about scalar evolution. So remember that the helium-4 abundance looks like, depends on the ratio of the neutron to proton numbers. And so we can calculate this. So the theoretical prediction for this, that is given by this number here. It's also measured observationally, and it's given by this number here. So then we can look at what the difference between the experimental measured value versus the theory prediction is, and we get some number. And if you actually go through and kind of plug in what goes inside here, it turns out that this depends on the change in the neutron to proton ratio at the week during freeze-out, the relative change of that, minus this is the piece that depends on the neutron decay lifetime. Okay, so the change in the helium-4 abundance is sensitive to changing the neutron to proton ratio as well as changing the neutron decay lifetime. So these are the knobs that you have. Okay, so let's look at this bottom piece here. So here's what the relative change of the abundance looks like, what it depends on. And so let's look at this piece first. So what is the change in the neutron to proton ratio at freeze-out? Well, this depends on the Z mass, the W mass, and the mass difference between neutrons and protons, right? Because this is set by the weak interactions. What do the weak interactions depend on? Depend on the W mass and the Z mass, or the Weinberg angle. Interchange these. Right, so we have these, the decay lifetime of the neutron depends on these factors here. So the change in the, so I switch from capital delta to small delta, it's the same thing here. So the neutron and proton mass difference, changing the electron mass will change this, changing the W mass will change this, changing the Z mass will change this. But because I'm looking at this case where I have a scalar that has this universal coupling, and remember this coupling coupled to the mass terms in the standard model in the same way. So all of these terms, well, this goes to 0 because they're the same. And we can pull out the phi squared over lambda squared for all of the rest. See, all of these are going to be the same dependence on phi squared. Makes sense. So by making that observation, because we're looking at this simplified case of the universal coupling, we can see that the change in the helium-4 abundance depends on this phi squared over lambda squared in this way. Okay, so just to repeat, we're interested in seeing how the scalar is going to change the prediction for the helium-4 abundance. And the way that it comes into changing the helium-4 abundance is by affecting the masses that are of the center model particles. And so by turning the crank, you see that this change then depends on this phi squared over lambda squared term times these factors here.
Is it dominated in practice by the changes in the vectors? It kind of looks that way, but there's like a
yeah, because it seems like this is the biggest. This piece and these pieces are.
Yeah, so it's probably pretty similar if you turned off. And conversely, if it was only for some reason only coupling to fermions, it would be less, I guess. It seems like it would be interesting to know that. Just
yeah. So yeah, in fact,
I mean, it's fine to have a simple model, but it's also just be interesting to know how much does it depend on that.
Yeah. So in fact, I was maybe a bit too quick in the beginning. So this has been looked at by Evgeny Stadnik and Victor Fombaum, where they didn't look at universal coupling. They let the lambdas for the vectors, the fermions, and they also had one for the photon, vary so that they weren't related to. So it's what you're asking. And it did turn out that the vector case was the most important. So the reason why we revisited this, so I think my title probably should have said like revisited constraints, is that they didn't take into account the fact that the phi also received this correction to its mass. And when they did the scalar evolution, they didn't do it as carefully. So we were interested to see how it would change if you took those factors into account. Unfortunately, it doesn't. Well, fortunately, unfortunately, it doesn't change it by very much. But I trust our balance. Yeah, because the other thing, in fact, I think the changing the photon coupling, changing alpha, has a huge effect. And for us, it's a higher order correction. It comes in through a loop. So for us, it's not a big effect. But it is true, the vector case, the vector coupling is what's really driving everything. Okay, so now I have how this change in the helium-4 abundance prediction depends on phi squared over lambda squared. And so now I can set a constraint on my mass claim. Okay. And so I get something that looks like this. So what I'm showing here is on the x-axis is the mass of phi, mass of the scalar, versus the scale capital lambda on the y-axis. And here's this curve here. So what this curve is telling you is that if I had, say, a scalar mass of 10 to the minus 15 eV, who had a scale of 10 to the 10 GeV, I would have made a large enough change in the predicted helium-4 abundance that it would no longer match with observation. And so because we have some observational number, this is rolled out. Right? So basically we have to live up here in this thing. Yeah, so what I was just saying was this paper here by Stadnik and Fombaum looked at this case without taking into account the effective mass, or what I mean by reheating is the fact that you have this E plus E minus little bump in the baryon density evolution. And they get this blue curve here. So in fact, they're actually they set a stronger constraint. So it's not quite as strong as what they had calculated. But it's a similar, I guess it's log scale, so you could say it actually is a big effect because you can see it by
There should also be another constraint that over on the right side of your plot, just from star cooling. Right?
Yeah, so I'll show at the end all the different other
Okay,
constraints
good.
that will
Yeah.
come up, which has been interesting. And there's a few more that I'm still trying to figure out if they actually apply. So maybe this is something would be interesting to talk about. Okay, so this was an analytic constraint on the helium-4 abundance. Turns out for this, and you might want to ask, can I look at the other elemental abundance? For example, does deuterium tell me anything about what phi can be, or does lithium tell me what it can be? Turns out that these other elements are a lot trickier to do because they do depend on nuclear reaction rates. And because we're changing the masses, you can say, okay, then I have to at each step change the masses of all the different particles going into these nuclear reactions, and this sounds like a mess. I don't really want to do it. But in this particular case, where we have this universal coupling from this conformal scaling, so remember our metric gets this shift, we can just change frames. So what I mean by that is everything I was doing before is something we call the Einstein frame, which then manifests itself as couplings of the scalar to the standard model. We can switch into something called the Jordan frame, where we change the metric, but we leave the standard model alone. And if you go through and work through it, what this ends up being is dependence on the Hubble parameter as a function of phi in that. And it turns out there's a numerical code for calculating BBN abundances, where one of the options is to change Hubble. This is fantastic. This makes our life a lot better. So what we needed to do was to calculate what is the Hubble at a given time. And you can make a little table and then just run the code through this. So that's what we did. The code is called Ultrapeepi. I should put a reference for it. Alexander Arby is one of the authors of this. So it's a nice code that gives you the elemental abundances from BBN. And so what we get is this blue line. So this is not easy to see. So let's zoom in a bit. And so this dashed line here is the old Stadnik-Flambaum constraint. The red line is the constraint from our analytical calculation. And the blue line here is the numerical one. So it improves or it strengthens the constraint a bit by doing that numerically. Okay. And so now that we have this Ultrapeepi code running, it also calculates the abundances for the other elements. So we said, okay, might as well take a look at that. So we can look at deuterium. So here's deuterium, also not easy to read. So what's going on here? So deuterium, so what we're showing here is the blue line, which is the topmost one, is the numerical helium-4 constraint. The red line is the analytic helium-4 constraint, and the purple line is the deuterium constraint. So the deuterium constraint is still weaker than helium-4. We also made an interesting note that it actually shifts. So there's this discrepancy between the prediction for the lithium abundance versus what's observed. And turns out if you add in this phi, it shifts it in the right direction. But if you want it to make things match, then you screw up these other. So at first we're like, oh, maybe we can solve the lithium problem with this. Turns out you can't. Okay, so getting to what Marcus was getting at is, this is a scalar field that couples to the standard model. There's other searches for such a particle. So let's look at this. So right now I'm just showing you the BBN constraints. So let's look at how these other constraints compare to this. So one constraint comes from supernova cooling. So here is a supernova. This is what my cartoon of a supernova is. And within the supernova, we have nucleons. And because our phi couples to nucleons, it can bram off phis inside the supernova. Supernova has a lot of nucleons, and the nucleons will bram off pairs of phis, which then cause the supernova to lose energy. So we know roughly what the luminosity of the supernova are. So you can set a limit on how much energy these phis can be pulling away from the supernova. And this is work done by Maxime, who has thought a lot about these things. It turns out everything he's kind of already done at some point. So using this supernova cooling constraint, you can set a limit on the bound of lambda. It turns out to be independent of the phi mass. just depends on lambda, and it means that lambda needs to be above 14.5 TeV to be consistent with the supernova.
Question, is this assumed as free streaming? Or,
Yeah, I think it was a fairly simplistic way of calculating how things go. So I guess if you wanted to do it more
I
carefully.
mean, if it's independent of mass, it has to be pretty much in the free streaming. Because if you have-
Yeah, because we're looking at such light phase.
Mhm.
Yeah, you can effectively take them because the same process happens in the standard with neutrinos. So it's a similar thing to that. If they got heavier, then you would have to
worry about
worry about other effects. Yeah, that's right. Okay, so this is one constraint. Another constraint comes from fifth force. So you can say, oh, ultralight scalars, this will mediate a long-range force. These are really highly constrained. And in fact, they are. But in our case, because we're looking at a phi squared coupling, you need to send two phis between our test masses, right? So here's two test masses. They look like M&Ms, but they're test masses that will feel a force between them that's mediated by this scalar field. And so if you only had one, this goes like 1 over r, and these are very strongly constrained. But when you send two quanta between our test masses, this potential goes like 1 over r cubed and 1 over lambda to the fourth, and this is much less stringent of a constraint. In fact, it's less stringent than the supernova constraint. So this requires lambdas of above 2 TeV. So what does this look like? So I'm going to flip my plot over. So the x-axis is still the scalar mass, and now the y-axis is 1 over lambda. I like to plot it this way because then I can think of it as being a coupling strength. And also when you look at plots for like axions or Alps, they tend to plot it in this way. So saying that lambda has to be greater than a certain value means that everything that's 1 over lambda has to be below a certain value. So the astrophysics, meaning the supernova cooling, and the gravitational tests, so this test body changing the gravitational interaction between two test bodies, rules out this line here. And of course, because the supernova constraint is stronger, it's being set by the supernova constraint here. Another constraint you can have is through the CMB. So in the CMB, we have like Thomson scattering between photons and electrons. And this Thomson scattering cross-section depends on alpha and ME. And so in our scenario, we're changing the mass of the electrons, and so then this will change the Thomson cross-section, which will then change the mean free path of photons during recombination. And this will imprint itself on the CMB. Okay, so here's photons scattering off with electrons. And so there's this paper by Jens Struve and Hart, where they set a limit using the Planck data from 2015, saying that the change in mass of the electron has to be less than 4%. So using this, you can set a constraint on lambda, which in this case depends on m phi, of 0.6 eV squared over m phi.
So I can I just ask, so if these masses are really on the small side, are they, so is this assuming that you're averaging over the oscillations of phi? I just want to understand the physics here.
Yeah, so you're assuming...
Because phi is dark matter, so it's oscillating.
Yeah, so it has to be
And what I'm
oscillating.
worried about is it seems like for the very, very light case, it's oscillating very slowly, compared to
the
time scales at CMB. So I'm just wondering, there's no dependence on the phi mass? Is
So
it
this-
always oscillating slowly for the
Yeah, so
these
this,
light
actually, it
phis?
does have a, I don't think I would note it in my plot. There is a limit on when this.
Because it's basically frozen. I guess the point is, sorry, I'm just thinking out loud, but I guess it's frozen until the Hubble gets to be awarded the mass of the,
Right.
right? But I thought in this range,
So we always
Hubble
want it
is
to be
always-
oscillating. For one.
Yeah, but I
Like
thought
we
that this
oscillate.
range was so wide. I mean, maybe it's the very, very smallest masses. Is it oscillating fast enough? But what I'm wondering is, which regime are you in? Are you in the regime where there's a time scale set by m phi, that's the scale where it's oscillating, right? Assuming that Hubble is less than that amount. During the CMB, are you in the regime where it's oscillating fast, or it's stuck, or what?
should be oscillating. It should be oscillating faster.
I guess I'm just surprised that that would be the case all the way down to the very smallest. Maybe it doesn't matter for your, but you know, you're going, because the smallest M5s you're considering is 1 over M5 is like the size of a galaxy.
Yeah.
It's, you know, it's a
Pretty big.
It's a big, yeah, big.
But at early
Time
times
scale,
it
light
was
scale.
oscillating smaller. Oh, it was oscillating faster.
That depends on lambda.
Depends on lambda. So you always want to be in a regime where it's oscillating. So you can also set. I don't do it in my.
Anyway, you get a very, well, let's see, EV squared over M5. I don't know, why don't you show, maybe it doesn't matter. Maybe you can
Yeah.
show
So this
it.
is
Show that line.
this is where that line.
It is relevant for the very smallest lambdas. So my guess is you're actually just stuck, you know, like if you're assuming there's alignment. I don't know, okay.
Yeah. So this is actually one thing that I'm still trying to figure
Yeah, I
out.
would just like to know what the basic physical picture is here. Oscillating?
Because you do want to have things oscillating, otherwise it's not dark matter. So that will also set a size of.
Yeah, but just early on, it's stuck, right? That's the Hubble-dominated case when you're.
So the Hubble-dominated case, we never. It's like over. What was it? It was like down here. The Hubble-dominated case is.
So you're saying it
further.
is oscillating there?
Yeah, it's always oscillating. For
Okay,
us.
so then can we go back? Sorry, then can we go back? I'm sorry, but I just would like to understand this. So if it's oscillating, then why? Then it's saying that it's just changing the mass of the electron in some oscillatory way.
Well, I guess so. Maybe it's the phi is oscillating, but it's oscillating slow enough compared to the rate that the scattering is happening that we can consider phi to be constant.
I thought
I
that the
think it's
scattering
the-
was happening at the Hubble rate, and that's what defines the CMB, right? Is that the photons are decoupling, so their scattering rate should be comparable to the Hubble, I would think. We can discuss this later, but I mean, I don't want to just stop your talk dead, but
Yeah, it's something that I should also. This is the one piece that I'm the least
okay.
comfortable with.
Did you change alpha?
So we don't change alpha. In principle, you do change alpha because you can close the fermion loop and then add 2 photons. But this is going to be highly
Phi dependence
suppressed.
is a scale transformation, so it would be a one-loop effect. Right?
So it's-
Your phi
yeah.
dependence is like a scale transformation.
Right, exactly.
So you get a one proportional to beta.
Yeah, so it's there will be a change to alpha, but it's going to be much, much smaller than this. For like lambda to the 1 over lambda to the 8 is what it goes like. So initially we were thinking, oh, we should look at that too, but it turned out to be a small effect. Okay, and so on the low end, you can also set a lower limit to what masses we're interested in, because we want this phi to be dark matter. And so like Marcus was saying, we want things to fit inside a dwarf galaxy. We know dwarf galaxies have dark matter. So you can set a lower limit on the size of the mass, because you want the wavelength of this guy, this scalar, to fit inside the smallest of the dwarf galaxies, which are about a kiloparsec. So using this, you get a lower limit of about 10 to the minus 22 eV. And so this mass, scalars in this mass range are often called like fuzzy dark matter. So you can set a lower limit, so that sets that line there. There's one more. Yeah, I think we just look at one more constraint, which is looking at binary pulsars. So here's a binary pulsar system. So pulsars are neutron stars that are rapidly rotating and then are emitting off jets. And so if this binary pulsar system is in a field of dark matter, the scalar dark matter, you will get variation in the orbital period of these binary pulsars because the masses of the objects that are going around are also changing. And so the orbital periods of pulsars are measured fairly precisely. So using the fact that we can measure what the orbital periods are, you can set a constraint to how much these masses can be changing. And so by looking at various pulsars, you can set these constraints. So these dots, so let's look at the black ones first. these dots are different binary pulsar systems. And using their measured orbital periods, you can set constraints that you need to be below these dots. And so these are for some given precision. The gray ones are if you were able to measure these periods with the currently most precise measurement. So these were not measured with that, but if you could do that, you would be at this where these gray dots are. Okay. So where does this compare with the BBN constraints? So the BBN constraints are these this red shaded in region here. So here's the. It's a bit hard to see. The pulsars are here. The CMB is here. The fuzzy dark matter is here. Astrophysics is up there. This skinny dashed line is the Stadnik Flambaum result. The thick dashed line here, which is the inner Moore line, is our analytic constraint from the helium-4. And the thick solid line is the numeric helium-4 constraint. So there is one more constraint that I think I've convinced myself does apply, and this is with superradiance. So with scalars of around this size, you can have an effect called superradiance around black holes, where if you have a black hole and it has this cloud of scalars around it, a spinning black hole, the cloud of scalars will slowly pull angular momentum from the black hole. So this will change their spin down rate and also affects their lifetime. So there's been a series of papers by Masha Baryon, one of the main authors on these, and Samina Taki, where they set constraints on, and this is a purely gravitational thing, so it only depends on the mass. So you can set constraints on observations of black holes that say that you cannot have scalars living in these bands. Otherwise, these black holes would have spun down more than what we see.
So is that 3 different black holes you've shown?
There are 3 different populations of black holes. So there's like stellar mass black holes. So the mass of the black hole sets the size of the wavelength that you can probe. And so the smaller ones probe the heavier ones. And these are, I think, the supermassive black holes. More massive black holes. The reason why I wasn't quite sure if I should put these on is if you have self-interactions within the scalar field, you get something called a bosonova, where the cloud kind of collapses down against itself and it dissipates, and is no longer around the black hole, so it's no longer pulling angular momentum. And that's actually a fairly strong constraint. So in the case of self-interactions, I think these completely disappear. But I think there's a way to, because I would get self-interactions all through a loop effect. So I have a phi, and I close the loop and put 2 phis. But I think within the Lagrangian, you can always add a bare phi to the 4th that cancels. Maybe you have to do some tuning. So I think you can get around this self-interaction.
Isn't there also, there is some constraint on the self-interactions for it being dark matter, I remember.
Yes.
Right, so
Yeah.
you can't have,
You need it to be oscillating.
it has to be sufficiently, the self-interactions have to be sufficiently weak, otherwise it also screws up dark
Yeah.
matter distributions.
Yeah, and
right?
it needs to, you can calculate with the Jeans length, which the Jeans length is, which affects structure formation. And so if the self-interactions are strong enough, it'll affect structure formation below a certain size. So if you do that with just the self-interactions from this loop effect, those were actually here, which was actually the strongest constraint. And
From the, so you're saying, so the Jeans length, you're saying, the Jeans length for ordinary matter or the Jeans length for dark matter?
the Jeans length for the dark matter
Is affected, I see. So on this plot, you're saying that these self-interactions are strong enough to affect structure formation in a large part of this plot?
Yes.
I see.
But I was talking with Pratik Agrawal, and he was saying you can always get kind of model build your way around. You tune your way out of those self-interactions. So this is one, the last thing that I want to understand better, if that's actually true. Because if it's not true, then superradiance disappears, and then the Jeans length requirement is the strongest constraint.
Okay.
But okay, so that's more or less what I have for today.
Any more questions?
I'm just like wondering a couple of suggestions if you
Yeah.
look into the cooling of red giants and solar emission constraints, they might give you something.
Yeah, I think
Although
the
I'm not
supernova
sure.
constraints were stronger. So this Olive Pospelov paper
Mm-hmm.
from 2007
Yeah.
really goes through all the different constraints, and they're the supernova ones were the strongest. So they also mentioned stellar
Yeah,
constraints.
because usually like supernova, there's only one region of couplings where it's actually relevant. If you're talking about SN87, then
Yeah,
triple
so you need to be
Right.
below the temperature of
Yeah, so
below,
also something else you might look into for the slightly heavier mass. There's the LEP monojet searches, but they might not be that strong. I mean, they're usually about MeV range couplings, MeV range masses, and like
Okay, I thought they
stronger
were a little
couplings.
bit-
Although I'm not sure if it's going to give you like.
I thought left was a bit higher.
I think they'll be always weaker than asphalt. Well,
Uh,
those will cut
It's
off.
around
Yeah, so
around
these will cut off.
around the top, but I'm not sure. That's why I'm saying I'm not sure if it's going to give you
That's true.
anything.
The
That's worth
temperature's
looking
at
into.
KeV, so you should really cut off the.
Yeah, and in fact, this one should
But they're,
stop.
but he's only, they're only going up.
Yeah,
to-
I mean that's where.
Stop.
They're only going up, yeah.
Yeah,
so-
somewhere around that.
Yeah, so if we were to extend this plot, then all these collider things would accelerate.
I mean, even at 1 MeV it would still appear, but
Okay,
you
yeah,
want to
that's
clip
good.
it.
I should check to see where those come in. For sure.
If there are no further questions, let's thank Tien-Tien again.